objective and spectroscopic method. As can be understood from the above-mentioned examples, many spoofing techniques against biometrics authentication systems make use of an artificial or non-human material, such as a plastic fingertip, contact lens, copy medium, etc., to provide a false biometric signature. In view of this, the author considered that biometrics authentication systems can be significantly reinforced against spoofing by incorporating a means that enables judgment not simply of aliveness but judgment that an object being presented for authentication is a portion of a living human being that is free of any intervening artificial or prosthetic material. An object of this work is therefore to provide a method and a system that enhances existing biometrics technology with a spectroscopic method in order to prevent spoofing. It goes beyond the simple approach of aliveness detection and proposes the implementation of verification of spectral signatures or spectral factors that are unique to human beings or a predetermined class or group of human beings in addition to currently employed methodologies in a multi-factor manner to reduce the likelihood of an imposter getting authenticated. Another aim of the work is to provide methods and systems that augment two widely used biometric systems, fingerprint and iris recognition devices, with spectral biometrics capabilities in a practical manner and without creating much overhead or inconveniencing the users. Spectroscopy refers to a method of examining matter and its properties by analyzing light, sound, or particles that are emitted, absorbed or scattered by the matter under investigation. Wikipedia, 2011. A multiple biometric system employing spectroscopy can make spoofing very difficult and time-consuming, if not impossible. This is because a spectroscopic approach using various wavelengths allows us to examine various parameters of skin, underlying tissue, blood, fat, melanin pigment in eyes, etc. that vary from person to person, and makes spoofing a very difficult task of imitating multiple physiological characteristics. Skin is a complex biological structure made of different layers with distinct morphologies and optical properties. Conventionally, it is described by dividing it into two major layers. The inner layer, or the dermis, is between 1 to 4 mm thick and consists mainly of connective tissue composed of collagen fibers. Other dermal structures include nerves, blood vessels, lymph vessels, muscles, and gland units. The outer layer, the epidermis, is typically 40 micrometer thick, but it can be much thicker on load-bearing areas such as palms and soles. When we look at light reflected from the skin, we usually see two distinct reflection components, a specular or interface reflection component ELS and a diffuse or body reflection component Pound, Schaefer, 1985. The specular or interface reflection occurs at the surface and in only one direction, such that the incident light beam and the surface normal are coplanar, and angles between incident and reflected light are equal with respect to the surface normal. As shown in Figure 1, not the entire incident light is reflected at the surface and some penetrate into the skin. The refracted light beam travels through the skin, hitting various physiological particles from time to time. Within the body, the light rays repeatedly get reflected and refracted at boundaries that have different refractive indices. Some of the scattered light ultimately return to the surface and exit from the skin in various directions, forming the diffuse reflection component Pound. This component carries information about the person's skin color and his/her unique biological spectral signature. Using the two-layer model, Otsuki and Healy, 1998, determined the surface reflectance, which takes place at the epidermis surface, to be about 5% of the incident light, independent of the lighting wavelength in the human race, Anderson and Parrish, 1981. The rest of the incident light, 95%, enters the skin and becomes absorbed and scattered within the two skin layers. The absorption is mainly due to such ingredients in the principle of body reflectance. Blood as hemoglobin, bilirubin, and beta-carotene. Figure 2a shows a spectral reflectance curve of a typical Caucasian skin, Anderson and Parrish, 1981, melanoma, 2006. Figure 2b shows an exploded form of this spectrum into its distinct components, namely, epidermis and hemoglobin. There are also spectra of water and collagen substances, but these do not play a significant role in the indicated wavelength range. As can be observed, the melanin in the epidermis absorbs the most part of blue light at 470 nanometers, and hemoglobin absorbs green light at 525 nanometers and red light at 640 nanometers. Also, though not shown, Near-infrared light at 850 nanometers is used to identify papillary dermis, melanoma, 2006. A typical Caucasian skin spectrum and its distinct components, melanoma, 2006, A. Typical Caucasian skin spectrum, B. Its distinct components.